All right, let's take a look at calculating the reaction rate of one reactant from that of another. So we learned about reaction rates. We can write a balanced chemical equation. We can see that we can use a fraction typically to adjust for that stoichiometric coefficient in front of a balanced chemical reaction. Now, a question like this builds upon previous knowledge and incorporates this new knowledge. So not only are we doing reaction rates, but we're also doing what looks like ideal gas law. We're given a liters per second, we're given a temperature, we're given a pressure. Now we have to calculate rate anytime we're doing a rate or some sort of stoichiometry, we have to find moles. So the first thing we're going to do, first thing I'm going to do is first balance this equation and then calculate how many moles are being used per second to figure out how much dihydrogen or H2 is being produced. So let's write this. So this is not our typical combustion, which we have with methane. So we have actually CH4 reacting with gaseous water, so steam, and it's going to produce carbon monoxide and hydrogen gas. Now we got a balance. We got lots of hydrogens on the left side, so we got 6, and then 1 oxygen on both sides, 1 carbon. So actually all we need is a 3 here. 6 hydrogen on both sides, 1 carbon, 1 oxygen. So there's our balanced chemical equation. So we could say the rate that CH4 is being used up is equal to 1/3 the rate of hydrogen being produced. But let's figure out how we calculate this. So the first thing I'm going to do is solve for moles from my ideal gas law. So I have a pressure, 0.12 atm. I have a volume, 649 liters, and that's per second. I'm going to keep that in there. My gas law is 0.0821. And my temperature is 217. I'm going to keep the 0.15 right now. 490.15. I'm going to put that in. What is that equal to? Let's do. So I get N equals 1.935 moles per second. And so I have my atmospheres cancel, I have my liters cancel, I have my Kelvin cancel, and I'm left with moles per second of CH4 being used up. So 2 ways I can go about this. One, I can use the fraction. The other is to do a stoichiometric ratio. So I could say, well, there are 1 mole of CH4 for every 3 moles of H2. And so I could calculate that and say there are 5.806 moles of H2 being produced for every 1.93 moles of CH4. The other way would be to say CH4, the rate of CH4, so negative is equal to 1/3 of H2. And so then I would solve for the rate of H2 by multiplying by 3. So -3 concentration of CH4 is equal to H2. And so I would say I'd put in this would be a negative 1.935 because it's being used up. Now I use it as a positive over here, but again, a lot of times the negatives are we're just taking a second to think about them. Okay, yeah, it's being used up. So that negative times 3, and you'd get that same number. Either way, works, same number. So now we have moles per second of H2, but the question asks for kilograms per second. So I'm going to have to say, well, for every mole of H2, there are 2.02 grams. And then for every 1,000 grams, there's 1 kilogram. And I get 0.01173 kilograms per second. So decent amount of volume, likely, but a small amount of kilograms because it's gas here. So let's figure out significant figures. It looks like we got 2. It's also telling me 2. So I'm going to go with 0.012 kilograms per second. So I can try that. I could also try times 10. We got a times 10 here. So I'm going to go with 1.2 times 10 to the negative 2. There we go. So a little bit more than just balancing this reaction rate, right, which was just highlighted right here, that 3-to-1 ratio, but we had to calculate moles first, then we had to calculate 2 kilograms per second.